So we're officially done with apportionment. So we finished that right before break. We're going to start on chapter 9, which is about sequences and how populations grow. And so we'll have a few days on that. And then just to remind you that your apportionment project, the Excel project, its due date is coming up April 5th. Okay. That is, yeah, a week from today. Yeah, 1 week from today. So that project, again, is completely digital. There's no paper handout. So it's posted in Moodle. It's a completely digital project, no electronic version. There's no paper version. It's project 2. You click on it in Moodle, and there are several video tutorials to help you through it, right? So that's what these things are first. Then there are several sample Excel files that you can study if you still are confused after the video tutorials. And then the last file this is project 2. That is the actual project. So when you click that, open it, you have directions on the first tab, and then there are 5 more tabs along the bottom for doing the 5 apportionment methods for the House of Representatives based on each state's population. All right. You submit it via email because I want to see your digital file, right? Because I'm going to grade it based on the fact that you have to do all of this using formulas in Excel, not by hand. And if you try to do it by hand, you know, it would feel really terrible because it would take you a really long time. So I need to be able to click on any given cell, and I will look up here to see what you wrote for a formula and make sure that it's correct. So this is submitted via email. That's part of the directions, right? So save the file on your computer and then use formulas to apportion the 435 seats among the 50 states using each of the 5 methods. Every cell in your spreadsheet needs to be calculated with a formula, except for the given populations and the modified divisors. And then you email me your completed project, right? Attach your completed project. So there's no paper for this project at all. Paperless project. All right, so that's what's coming up. And then once we finish chapter 9, we spend 1 day on chapter 13. And then we'll have test 2 coming up on the 19th. So it's a little ways away still, but just looking ahead, it's coming. Okay, anyone want to go over anything from apportionment before we jump into chapter 9? You had homework from Thursday, yeah. Yeah, due today, yeah. Okay, so let's say you have a round, flat cake. It's a mathematical cake, so it's completely flat, not a real cake. With one straight cut, like this first picture here, one straight cut, like this. Like this first picture. Okay. You can cut the cake into 2 pieces, right? And I just put the cut in a random spot. So they're not 2 equal pieces, but 2 pieces, right? Okay. So with 2 straight cuts, how many pieces can I cut the cake into? 4. Good. So put a 4 there. If I make 3 straight cuts, like in the third picture, how many pieces of cake can I get? 7, yeah. Yeah, so 1, 2, 3, 4, 5, 6, 7. And again, they're not all equally sized pieces, but I just want to get the most pieces possible. So I'm kind of making my cuts in such a way to produce the most pieces. All right, so I've got 7 there. How many pieces if I make 0 cuts? 1, there's just 1 big cake, 1 piece. 1 hungry person. Okay, so then if I make 4 cuts, I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pieces, right? Okay, so we want to try to find a pattern here. I would like to know how many pieces I can get if I make 10 cuts. So discuss among your group. You can draw more pictures if you want, or you can study the list of numbers and try to find a pattern. I think it's completely fascinating the different ways that people see this pattern. So I saw at least 3, and I think I only talked to like 3 people. So, so the first one that I saw people recognize was how much you add to get from one number to the next, right? So what do you add to 1 to get 2? 1, okay. What do you add to 2 to make 4? What do you add to 4 to make 7? What do you add to 7 to make 11? 4. So do you see a pattern among what you're adding? 1, 2, 3, 4. So the next number I would probably add would be 5, and I'd get 16, right? And then the next number I would add would be 6. 16 plus 6 is 22. Okay, and then the next number I would add would be 7. 22 plus 7 is 29. Then I'm going to add 8, and I get 37. And then I add 9, and I get 46. Then I add 10, and I get 56. All right, so that's one pattern that I heard several people talking about this pattern, but there were other patterns too. So one pattern that people noticed was if you add these 2 numbers, you get the next number in the list, right? So 1 and 1 is 2. 2 and 2 gives you the 4. 3 and 4 gives you the 7. 7 and 4 gives you the 11. 11 and 5 makes 16. 16 plus 6 is 22. 7 plus 22 is 29. See that pattern? All right, that's good. All right, and then there was another one. I'm going to clear out what I've written here because it's going to get messy. Okay, so the other one that people saw was if you add up the number of cuts and add 1, you get the number of pieces of cake. So like 0 plus 1, what is that? 1, and then you add 1 more and you get 2. If I wanted to know how many pieces, how many cuts I would get for 2, how many pieces I would get with 2 cuts, I would add up 0 plus 1 plus 2, which is 3. Add 1 more, and you get 4. Let's check it with a big one. Like, let's see if we can get the 16. Add up all these numbers. 0 plus 1 plus 2, that's 3. Plus 3 is 6. Plus 4 is 10. Plus 5 is 15. Plus 1 more is 16. So that's another way to get all the numbers. Let's see if we get the 56 if we do it that way. Add up all the numbers from 0 to 10. Then you add 1 more, and we'll see if we get 56. I'll use a calculator this time. Okay, 1 plus 2 plus 3 plus 4 plus 7 plus 8 plus 9 plus 10 plus 1 more, 56. So there are lots of ways we could have predicted that 56. Lots of ways you could have visualized that pattern. Good. All right, so we're going to be talking about lists of numbers for the next few classes. And a list of numbers is just the name for the mathematical name for that is a sequence. It can be finite. It could just have 3 numbers in the list, like 2, 7, and 20. Or it could be infinite, like 2, 4, 6, 8, 10, 12, 14, et cetera, right? So the numbers can be completely random. 2, 7, and 20 is a completely random list of numbers. I just picked them out of thin air. Or they can have a pattern, like in the second example, because I was listing all the even numbers there. So some notation that we're going to have to get used to with sequences is that we typically name a sequence with a letter. So for example, we would name this sequence 2, 4, 6, 8, which is the list of all even numbers, right? We could name that A. So we have A equals the list 2, 4, 6, 8, 10, 12, blah, blah, blah. We name the terms of the sequence, right? So 2, 4, 6, 8, those are the terms, we call them. We name them using the A with a subscript. So that's like in the lower right-hand corner. And the subscript tells you where in the sequence to look. So if I ask you what A sub 3 is, you would answer 6 because it's the third term in the list. Okay. So what is A5? 10. The fifth term in the list would be 10. Good. So the subscript is telling you where in the list to look for the number that I'm asking for. All right, so let's see if we can identify a pattern with this particular sequence A. We already know it's the even numbers. So if I wanted to calculate A2, what's A2? 4, right? That's equal to A1, which is what? 2 plus what? How much do I have to add to 2 to make 4? 2. So I need a 2 there. No, I'm just going to put a 2 for now. Yep. Yep. It is also A1, but you'll see where I'm going with it in a second. All right, so A3, that is 6, right? A3 is equal to A2, which is 4, plus how much more? 2. A4, that's 8. It's equal to A3, which is 6. What do I have to add to 6 to make 8? 2. Okay, so what do you think I'm going to put in this blank space here? 2. Yep. So A5, that was a 10. That's equal to A4, which is 8 plus 2. So the pattern I'm trying to get you to see is that every number in the list is the number before it plus 2, right? That's one way to visualize the pattern of the even numbers. To get from one number to the next in the list, we're always doing plus 2, plus 2, plus 2. It's just the previous number in the list plus 2 more. So the notation I use for that is I say, okay, well, the nth number in the list, like if I wanted to describe a generic term, I would call it A sub n, right? So any number in the list, random number n, is always the number before it. So how would I write a subscript that means the one before n? Caroline? N minus 1, yes. So my subscript just has to be 1 less than n. So I write it as n minus 1. And then I'm going to add to how much to that? 2. Okay. So this is a tricky, this is notation that takes a little bit of getting used to. Okay, so A sub n means a generic nth term in the list. And A sub n minus 1 means the term before the nth one, the term right before it. So we call this a recursive rule for a sequence. We call a rule recursive if it uses previous terms of the sequence to calculate the current term. If you need to know the term before it in order to get the next term, we call it recursive. So it's one way of visualizing the pattern of even numbers. Let's think about it another way. Same list, even numbers. A1. What is A1? 2. Okay. So to get 2, what do I multiply 2 by to make a 2? 1. Good. All right. A2 is a 4, right? So 4 is 2 times what? 2. And A3 is 6. That's the third number in the list. 6 is 2 times what? 3. And A4, that's an 8. 8 is 2 times what? 4. Okay, so let's see, before I try to write a generic formula here, let's notice the pattern between the subscript and the number I wrote in the line. It's the same, right? A sub 3 is 2 times 3. A sub 4, 2 times 4. A sub 2 was 2 times 2. Okay. So A sub n should be 2 times what? N. The subscript and the number you multiply by are going to match. So if I wanted to find the 20th term in the list, I would do 2 times 20, right? And that would give me 40. 40 should be the 20th term in my list. So this is another way of visualizing the same pattern. Okay. So the nth term, a generic term in the list, you can find by doubling its location. All right, so we call that an explicit rule for the sequence because I did not need to know any terms before it in order to calculate the value of a term in the list, right? So if I wanted to know the 100th term in the list, I could just do 2 times 100 and I would say, oh, the 100th term in the list is 200. And I did not need to know the 99th term to figure it out. So we call that explicit versus the one before, which was recursive. All right, so let's play a little guessing game here. So I have a rule that I used to create this table of numbers. Take 2 or 3 minutes in your groups and see if you can guess S5 and S0, and then we'll together come up with rules, recursive and explicit. Okay, so what pattern do people see in this table of values? 1.5. Okay, so it looks like to get from one term to the next here, you do plus 1.5. 1.5 plus 1.5 is 3. 3 plus 1.5 is 4.5. 4.5 plus 1.5 is 6. So 6 plus 1.5 is 7.5. So S5 is going to be 7.5. What do you think S0 means? It is 0, but in general, where is it in the list? Yeah, before it, because the term before the first term, right? Which kind of doesn't make any sense, but it means that what kind of goes right here, right? What came before 1.5? 0, because you have to go backwards in the list, so you subtract 1.5, so we get 0. Good. All right, so if I need a recursive rule, so that means I'm trying to find a generic S sub n, right? I'm trying to figure out how to calculate the nth term in the list. Recursive means I'm allowed to use the term right before it, right? So what term comes right before the nth term? N minus 1 would be the subscript for the term right before the nth, right? Because if I was trying to find S sub 10, I would use S sub 9, right? You just subtract 1 from the subscript. So you'd say, okay, the nth term, the generic nth term, is calculated by taking the term right before it, which we denote S sub n minus 1. And then what do I do to the term before it to get the next term? Add 1.5. That is my recursive rule. Right, so the notation is difficult, but you can also, it helps me sometimes to just write like a sentence in English that I would say, okay, the nth term is the term right before it thank you, plus 1.5. Okay, and then once you have it written in English, you can kind of translate it to this brand new notation that we're working with. The nth term, we just denote S sub n. The term right before that would be an S with an n minus 1 subscript, and then plus 1.5. Yeah, Allie. Yeah, you might also, yeah, we'll do some examples where you also might use the 2 terms before it, right? Yes, that is the rule to get the term right before you use an n minus 1. Yep. All right, so for my explicit rule, again, I start with an S sub n equals. I'm trying to write a formula for the nth term, S sub n. But I'm not allowed to use the terms before it now. Now, when I write my formula, I'm only allowed to use the value n. Okay, so now I have to be able to look at the n value. All I can look at is the n value, and I need to use that to get the S sub n value. Okay, so if I know 1, I have to be able to calculate 1.5. If I know 2, I have to be able to get 3, right? So how are these numbers related? N plus 1 times 1.5. Great, yeah. So if you take the n term and you multiply by 1.5, right? So 1 times 1.5, take your 1. If you multiply by 1.5, you get 1.5. 2 times 1.5 is 3. 3 times 1.5 is 4.5. 4 times 1.5 is 6. 5 times 1.5 is 7.5. So that pattern works. Yeah. Also think of it, if you got the recursive pattern, if you know the recursive pattern is that I go plus 1.5, plus 1.5, plus 1.5 to get from one term to the next, you could just say, okay, well, I'm repeatedly adding 1.5, right? What operation in mathematics is repeated addition? Multiplication. So you multiply by 1.5 to do the explicit rule.
Can you also do it where you like just divide the first number? Undivided by 5 divided by 2 5 plus 9.
That is equivalent to multiplying by 1.5. Yes. Yeah. Good. All right. So in number 7 here, this is a special kind of sequence. A sequence where the rule to get from one term to the next is to add or subtract a constant. In this case, 1.5 is our constant, right? Is called an arithmetic sequence. All right. Here's another guess my rule. Anybody see a pattern that they could use to predict G sub 5? Multiplying by 2, yeah. So when you take 5 and you double it, you get 10, right? 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. So 40 times 2 is 80. So G sub 5 we predict is 80. What do you think G sub 0 is? 2.5, yeah. Because to go backwards in the, if you go forwards in the list, you have to multiply by 2, right? So to go backwards in the list, you would have to divide by 2. So if I wanted to go over to the left here, what's 5 divided by 2? 2.5. All right, so if I want to write a recursive rule for G sub n, so I want G sub n equals, trying to write a formula here. And again, it helps to write this out in English, right? So the nth term in the list, so any term in the list is equal to the term before it times 2, right? So everybody saw that pattern, was able to say it out loud to me just now, right? Any term in the list is just the term before it times 2. So if I'm going to let G sub n represent a random term in the list, what notation do I use to represent the term right before that one? G sub n minus 1. Yep. And then times 2. Every term in the list is the term right before it times 2. Right. Recursive does not have to be only addition. The only thing that makes it recursive is that you use that n minus 1 script. Yeah. As sort of a general rule, writing an explicit formula is a little bit harder than writing a recursive formula. So if I want to give an explicit rule for G sub n, it might help a little bit if I'm going to rewrite my table here, all my values in it, 0, 1, 2, 5. So this was 2.5, 5, 10, 20, 30, 40. Oops. There's no 30. 20 times 2 isn't 30. 0, 2.5, 5, 10, 20, 40, 80. Good. Okay, so in the arithmetic sequence, we were repeatedly adding things, right? We added 1 plus 1.5 plus 1.5 plus 1.5. And we wrote our explicit rule that repeated addition translated to multiplication, right? Here, we're repeatedly multiplying by 2, right? What operation in mathematics corresponds to repeated multiplication? The exponent, yeah, like several people said squaring. They mean the exponent. Repeatedly multiplying is denoted with an exponent, right? Okay, so I'm going to rewrite G sub n here as using an exponent of times 2 to the something. So I don't have quite enough room to do this. Oops. Okay. All right, so I'm going to do 2.5 times 2 to the something. Okay, all of these numbers can be written in that form. So 2.5 times 2 to some power. 2.5 doubled a bunch of times. Oops. Times 2.5 times 2. How many times do we double it, right? All right, so my first number in the list is 2.5. How many times do you want to double 2.5 to get 2.5? 0. Yeah, we don't double it at all, right? Because 2.5 is the first is the 0th number in the list. Okay. If I want to get 5, right? My next number in the list is a 5. How many times should I double 2.5? Once. I want to double it once, right? I just want to do times 2 once. So I'm going to put a 1 in there. Okay. All right, and then if I want to get 10, right? My next number in the list is 10. If I want to start with 2.5, how many times do I double it? I want to get 10. So what happens if you start with 2.5 and you double it once? What do you get? 5. Double it again. What do you get? 10. It's 2. You want to double it twice. Okay. All right, now I would like to get 20. I'm going to start with 2.5. How many times do I want to multiply by 2 to get 20? So let's just go through it, right? I'll count on my fingers. 2.5. Double it once. What do you get? 5. Double it again and you get 10. Double it again and you get 20. So how many times did I double it? 3. Okay. Yes, yes. So that's the pattern. That's the pattern we're looking for. The ends are matching the exponents here. Yep. So, yep. So my formula is going to be G sub n is 2.5. Start with the 2.5, and then you double it n times. So times 2 to the n. So G is also a special kind of sequence, a sequence where the rule to get from one term to the next is always to multiply or divide by a constant. In this case, that constant was 2. I was doubling, right? Is called a geometric sequence. All right, so that's it for the demo portion of the lesson. We're gonna do the traffic jam activity as our group work today. So if you turn the page, traffic jam is the first thing here. So I want you to imagine that there are 7 stepping stones and 6 people. On the 3 left-hand stones, facing the center, stand 3 of the people. And on the 3 right-hand stones, also facing the center, stands 3 other people. And these are like teams of people, so they look different, right? The center stone is empty. The goal is that everyone must move so that the people who were originally on the left have to finish on the right, and the people who are originally on the right have to finish on the left 3 stones, okay, with the center stone empty. Okay. So the goal is to have everybody switch places. The rules for the moves you're allowed to make. Okay. After each move, each person has to be standing on a stone. You can't like just step off the stones. If you start on the left, you can only move to the right. There's no moving backwards. And if you start on the right, you can only move to the left. You can jump another person if there's an empty stone on either side, but you can't jump more than 1 person. And only 1 person can move at a time. So the question is, how many moves are necessary to reach the goal? So here's a really common way to approach a sort of difficult math problem, is to make it smaller, right? So let's think about what would happen if we only had 3 stepping stones and 2 people. I need 2 volunteers. Can you 2? Okay. I got 2. Actually, come on up, Max. I'll coordinate. Actually, come right over here. So I'm going to put down 3 stepping stones. 1, 2, 3. Oh, I only need 2 people. Sorry. Max, go sit down. All right, so each of you stand on a stone. Okay. All right, so I've got 2 people now and 3 stones. So I just shrunk the problem down from what I was working on before. Okay, so they have to switch places. Hannah can only move that way. Caroline can only move that way. Hannah, right? Okay, good. All right, and you can only move 1 stone at a time. You can jump someone if the stone behind them is empty. All right, so Hannah moved to the center stone. So let's keep track. That's 1 move, right? Caroline can jump her. That's 2 moves. And then Hannah moves to the last stone, 3 moves. Took 3 moves for them to trade places. Okay. Now I can make the problem bigger by adding a stone on each end, and I could have 2 people with 5 stones, right? 4 people with 5 stones, 2 on each end. Okay, so go ahead, you can sit back down. So rather than acting this out with people, you have little grids here. 3 stones, 5 stones, 7 stones, and 9 stones, I think. Yep. And I have little tiles to represent the people, red and white tiles. Okay. And then as you fill this in, we're gonna think about how many moves it took. So we just did the very first example. We had 1 pair of people. That's just 2 people total. And how many moves did it take? 3. Okay, so we'll fill in the table there. T sub n is the number of moves. I'd like to know definitely the number of moves for 2, 3, 4, 5, 6, and 7 pairs of people. Okay, so I'm going to have you try to play around. It's hard. The larger the problem gets, the harder it gets. I'm going to give each table some red and white tiles. You can use red for 1 set of people, white for another. And try to figure out how many moves it'll take.